over to doctors Paul Quam and then William Ampe to take over. So Paul, it's all yours.
Okay, thank you. So today I want to give a presentation on what's known as Bayesian statistics. And yesterday, what we went over is referred to as the frequentist perspective or the classical statistics. And so I want to, whoops, hit the wrong button here. There we go. Okay, so yesterday what we went over was the frequentist or the classical view of statistics and statistical analyses. So what I'm going to do is review that. So the first part will be what you essentially saw yesterday at the beginning, but I want to do that just to have it clear in mind what the differences are between the frequentist perspective and the Bayesian perspective. And then the rest of the time I'm going to actually do or go over some examples of Bayesian statistics in how they're used in specific context. And so I'm going to look at three different areas there where we'll look at diagnostic tests. And then I want to go over in some detail a published randomized study that looked at medications for epilepsy. And then finally to talk about probabilistic sensitivity analysis, or Bayesian sensitivity analysis, as it's sometimes called, and how that relates to doing cost-effective analyses. So as you will recall from yesterday, when we talked about statistics and doing research, we said that, oops, the basic idea was that we have a population that we're interested in, and then to do research, we draw a sample, which may or may not be random, from that population. And so our basic question, or what's important to know, is the sample representative of the population? And so I gave an example here where we have the concept of repeated sampling, which is the basis for the frequentist or classical view of statistics. And that is that if we were able to sample a large number of samples from our population, or to draw a large number of samples, that over a large number of these, or as we draw an infinite number of samples from the population, that the mean of each of these sample means will equal the population mean. But of course, when we do research, we only get one chance at it here, so we only get one research sample. But the statistics that we calculate are based on the idea that we could do an infinite number of samples from the population. And so I had this set of diastolic blood pressures. And so the basic idea of infinite sampling here is if we could draw a number of random samples from the population here. And then I had this slide that looked at a number of random samples that we drew from the population with a sample size of 5. So in each sample, there's 5 values, and then we calculated the mean of these 5 values. And as you recall, this is what we refer to as a sampling distribution. In other words, it's a distribution of statistics, whereas these individual values here, if we looked at their distribution, that would be a distribution of observed data. But when we talk about a sampling distribution, we're talking about a distribution of statistics. So like in this case, the mean. And then we looked at how we assess variability among our repeated samples. And so we could calculate the mean, and then we have a standard deviation associated with this, and then we calculate the standard error of the mean, which, as you recall, is the standard deviation divided by the square root of the sample size. So in this case, it's divided by the square root of 5. And then from that, using a normal or a t-distribution, one of our sampling distributions, our theoretical sampling distributions, we can calculate a lower bound and an upper bound of our confidence interval. And so, as we said yesterday, what this means is that if we sample an infinite number of times, that if we have calculated a 95% confidence interval, that the confidence interval will include the true population mean 95% of the time. And so we had examples here where we can see that a few of just this small number here, the confidence interval did not include the true population mean. And then we looked at how we would do hypothesis testing. And I had a couple of samples of a treatment and a control group, and we looked at how you would compare the mean blood pressure using a t-test between each group. And so then we talked about statistical decisions and the alpha error rate and the beta error rate. And so as we mentioned, the important one is our alpha error rate, which is indicated by the p-value that we get when we do our statistical test. And the 0.05 being significant if the p-value is less than 0.05 is, I guess we could call that an entrenched tradition, but it's actually an arbitrary cutoff point for being statistically significant or not. So if we had, for example, set our alpha error rate at 0.01, or being wrong one time out of 100, then if we got a p-value equal to 0.05, it would not be statistically significant. So in that case, we'd fail to reject the null hypothesis. So you can see that the alpha error rate, the p-value that we choose, that you choose is arbitrary, but as we mentioned, 0.05 is sort of what's typically used in the research literature. And so then we talked about what p-values are and what they're not. And the emphasis here is I want to say that you select your alpha error rate level, your p-value, before you do your statistical test. You can't do your statistical test and then say, oh, well, okay, it's 0.055, and so we'll call that statistically significant, which you could only do if that's what you had set your error rate at, your alpha error rate at, before you did your statistical analysis. And so the p-value is scaled as a probability from 0 to 1. And then we talked about what p-values are not. The probability that the null hypothesis is false, or the alternative hypothesis that it's true, or that it's an index of importance or meaningfulness. What a p-value is the probability that the result you got are a result of random sampling variability or chance. And so we interpret the p-value, whatever we've set it at, if it's less than or equal to that error rate that we've set before, then we can say we reject the null hypothesis. If we fail to reject the null hypothesis if our p-value is greater than the level we've set. Okay, so then getting into sort of the Bayesian statistics here and how they differ from the frequentist or classical perspective. So in the frequentist, the basis for frequentist statistics is the probability, or a probability is the long run frequency of random events over repeated sampling. And so in the frequentist perspective, the data that we collect are random, but the population parameter that we want to estimate is fixed. So for example, the population mean or the population proportion of a disease or whatever it is we're interested in. In the Bayesian perspective, though, probability, although it's going to seem similar, has a different interpretation. And so what probability means in the Bayesian perspective, it's an index of confidence that we have about the occurrence of an event. And we'll see what is meant by that and how that differs from the classical perspective. But in Bayesian statistics, then sort of the opposite is true from the frequentist perspective. The data are viewed as fixed because that's what you have, that's what you've collected. But the population parameter that you're estimating is random. You're going to treat that as a random variable. Whereas in the frequentist perspective, the parameter that you're interested in is fixed. In other words, there's a true mean or a true proportion in the population. So basically what we do in Bayesian analysis is pretty straightforward. So we have a prior belief about the occurrence of an event or a diagnosis, or if, say, one treatment is better than another. Then we're going to collect information, new information that we haven't had. And then based on this new information or our data that we have, we're going to revise our prior belief with a posterior belief or a new a belief or a new conclusion. And so just an example from of this perspective in real life. So basically clinicians or physicians, even though if they're doing research, they probably use their statistics are probably classical in nature, but their actual practice is really Bayesian in nature because, for example, if a physician has a patient on some medications and then they come in for their checkup, yearly checkup or whatever, and they get a new set of labs, then the physician may update the patient's medications based on current lab results. So that's sort of the, the basic idea is that you update your conclusions or your beliefs based on the information, based on the data that you collect. So Bayes' theorem actually goes back a long ways, even into the 1700s. So the, oops, I'm getting too many things here. So the idea that is that we have the probability of an event given the probability of some other event. And so the basic Bayes theorem or formula here is that the probability of event A given our knowledge of event B, which would be the prior information, is equal to the probability of A times the probability of B, given the knowledge of A divided by the probability of B. And this is the well-known Bayes theorem. As I say, it's been around for quite some time. So how do we then apply this? I want to give some examples here, and I'll begin with diagnostic testing. And so what I have here is sort of the classic 2x2 table of a test that's either positive or negative to determine whether a person has the disease, which is indicated by a positive if they have the disease or negative if they don't have the disease. And so the cells of our 2x2 table here are defined as if you have a positive test and you actually have the disease, and that's called a true positive. If your test turns out to be negative, but you really have the disease, you're positive for the disease, then that's called a false negative. And so one measure of our the accuracy of our diagnostic test is called sensitivity. And so that's calculated as the number of true positives divided by the number of true positives plus the number of false negatives, or as I've indicated here, TP divided by the sum of TP plus FN, or false negatives. Then specificity is the definition of the situation where a person is negative, turns out to be negative on the test and actually does not have the disease. So we term that a true negative. If they turn out to be positive on the test, but they really don't have the disease, and that's called a false negative. And so specificity then is the true negatives divided by the sum of the true negatives plus the false positives. We can also then calculate what we call predictive values, positive predictive value, PPV, or a negative predictive value. And so the positive predictive value is the idea that if we test and a person is positive for the disease, what's the probability that they actually have the disease? And so that's the true positive divided by the true positives plus the false positives. And that's our positive predictive value. Our negative predictive value is in relationship to those who test negative on the test. And so the negative predictive value is then if we test negative, then are they truly negative, or do they have are they false negatives? So specificity then is defined by the number of true negatives divided by the sum of true negatives plus the false negatives. And then so you can see here that we can also calculate the false positive rate and the false negative rate by looking at the false positive, that's divided by the false negatives plus the true negatives, and then the false negatives divided by the false negatives plus the true positives. So that's really the essence of a diagnostic test and the statistics that we can calculate from a diagnostic test, which in this case is the results of the test are either positive or negative for the disease. And so in words, what I've just gone over here is that sensitivity is basically the proportion of true positives that are correctly identified by the test. And specificity then is the proportion of true negatives that is correctly identified by the test. And our positive predictive value, then it's a proportion of patients with a positive test that actually have the disease. And our negative predictive value is the proportion of patients with a negative test that don't have the disease. And so it turns out that we collect some data, and then we can form and we can calculate our statistics based on that data. But the important thing or the important number is that in the population that we're interested in, what is the actual prevalence of the disease? And it turns out that when we calculate the sensitivity and specificity of our diagnostic tests, they're really independent of the prevalence in the population. However, the predictive values, positive and negative, are dependent on the prevalence of the disease in a population. And so what we can do then, using Bayes' theorem, is we can, if we know the sensitivity and specificity of a given test, then we can calculate the positive and negative predictive values based on the prevalence in our disease, in our population, which the prevalence of the disease we'd have to know what it is, or we'd have to speculate what it is. So this is our Bayes theorem, as I had on the previous slide, just stated in terms of diagnostic tests. So the probability of disease given a positive test is equal to the probability of positive tests given that you have the disease times the probability of the disease, which is the prevalence, divided by the probability of a positive test. And so in diagnostic testing here, our prior probability is the prevalence. And then our posterior probabilities that we're going to calculate are the positive and the negative predictive values. And so if we look at positive predictive values, then 1 minus the negative predictive value, they're the revised estimates. So these are our posterior probabilities that we want to calculate. And so we do that for, in this case, the probability of disease given a positive test. In other words, our predictive value of our test here, the probability of disease given a positive test. And so we can do our calculation here where we can have the same numerator that we did up here, but we can rewrite our denominator as the probability of the disease given a positive test times the prevalence plus the probability of a positive test given no disease times the prevalence. And so in words, what this turns out to be is if we take the sensitivity times the prevalence and then divide that by the sensitivity times the prevalence plus 1 minus specificity, and multiply that by 1 minus the prevalence, then we get a revised positive predictive value based on the prevalence in our population. And then we can do the same thing for the negative predictive values. It would just be specificity times 1 minus prevalence divided by 1 minus sensitivity times the prevalence plus specificity times 1 minus the prevalence. So let me give a concrete example here and actually put in some numbers for a test where we're getting an abnormal and normal test on some pathology. And so we have our test results here, whether they're normal, abnormal, or normal, and then the actual state of the disease, normal or abnormal. So we can calculate our different statistics here. So sensitivity, you remember, was the number of people that are testing positive that actually have the disease. And then we're going to divide that by the number that have the disease, which is the 231 plus the 27 that actually have the disease, or 258. So our sensitivity in this case is close to 0.9. Our specificity, on the other hand, is the number that are normal and have a normal test. So we divide that by the number of people that are actually don't have the disease, or that are normal as result from the perspective of their pathology. So that's 54 divided by 86. And so our specificity is about 0.63. And then we can calculate the prevalence, or the positive predictive value, by looking at the number who are actually have the disease and test positive for the disease, plus those who have a abnormal test but are negative for the disease. And so our positive predictive value here is 231 divided by 263, or about 0.88. And then our negative predictive value is our number of true negatives divided by the number that tests normal on the test, that test normal, have a negative test, and then are actually normal in the population. So that's 81. So 54 divided by 81. So our negative predictive value is about 0.67. So what this means is if we test an individual in this particular population, and they test positive for the disease, that is, they get an abnormal test here, then the probability that they actually have the disease is about 0.88. And conversely, if they have a negative test, then the probability that they actually have the disease is about 0.67. And so in this case, when we did our study here and came up with these numbers, we looked at a sample that had a prevalence of 0.75. In other words, there's 258 that are actually abnormal out of a total of 344. So the prevalence in our sample here that we obtained, the prevalence is 0.75, or 75% of the sample was actually had the disease, or was actually tested abnormal. So now then, based on Bayes' theorem, what if our prevalence was something different? We wanted to take our test here for positive or negative or abnormal, normal, and we want to apply it to a different population or a different sample where the prevalence is different. And so using our Bayes' theorem, then we can solve the equation for any particular prevalence that we think is applicable. And so, for example, if the prevalence is 0.5 instead of 0.75, then we calculate our positive predictive value here and find that it's about 0.7. So what this means is that if we, in this particular population, if we have an individual who tests positive for the disease or has an abnormal test, the probability that they actually are abnormal is about 0.7 or 70%. If we apply it to a population where the prevalence of the disease or the presence of abnormality is only 25%, then if we calculate our positive predictive value, we can see that it really decreases because the prevalence is quite low. And so now if in this particular sample or this particular population, if a patient has a positive test or test positive for the disease or abnormality, then the probability that they actually have the disease is only about 0.4. And so you can see that as the prevalence decreases, our predictive values, our positive predictive values really decrease. And I haven't gone through the example here, but you can see that if the prevalence it goes down or decreases in particular samples, that our negative predictive value is going to increase. So the point that I make here is that in terms of the Bayes theorem, that once we know the sensitivity and specificity of a diagnostic test, then we can calculate the predictive values given any particular prevalence that we might find or might estimate in a population. But the idea is that sensitivity and specificity always remain the same, remain equal, or remain the same regardless of what population you apply it to. So the second example of the use of Bayesian statistics I want to look at is a study on medications for epilepsy. And so there's, this is a randomized trial of 3 different medications for epilepsy. And so I want to go through this in a bit of detail because there'll be some new concepts here, and then how they apply Bayesian statistics to their research question here. So what they did in a randomized trial, and by blinded, that means that the investigators didn't know who was getting which drug. And it's an adaptive trial, and so we haven't really talked about that in terms of research designs, but an adaptive trial is basically can be either a randomized or non-randomized trial where we're going to, based on initial results, we may revise the number of patients that we're going to need in our study. And there's a whole branch of statistics that deal with how we handle adaptive trials. But so anyway, for this particular study, the primary outcome is the absence of clinically evident seizures. So that's a yes or no. And then improvement in the level of consciousness by 60 minutes after the start of drug infusion without any additional medications. So that's their efficacy that they're looking at. And then what they're going to do, they're going to make a prior assumption about the distribution in the 3 drug groups, and then they're going to, based on the data that they get, calculate the posterior probabilities that each of the drugs was the most effective or least effective. And then they also do an analysis of safety outcomes, but we're just going to focus on their efficacy outcome of the absence of seizures. So again, this is just restating their outcomes here. Of the primary efficacy outcome, the absence of seizures after 60 minutes of the drug infusion, which is what we're going to look at here. Okay, so again, they use what is called a response adaptive comparative effectiveness design. So they're going to compare the 3 drugs, and they're initially randomly assigned to receive one of the 3 trial drugs in a 1-to-1-to-1 ratio. Well, that means that all groups are going to be will be equal in size. But after 300 patients, then they're going to do take a look at their data, and they're going to see what it looks like, and based on that, they're going to then decide whether they should continue the study and enroll more patients, or whether they could actually stop the study because it's not going to show any difference. And that's what's called an interim analysis. And so they plan these interim analysis after enrollment of 4, 5, 6, and 700 patients. So at each analysis, then the random assignment probabilities were updated. So in other words, they may not be randomizing or assigning patients equally to the 3 groups. And then again, they're stratifying here by age, since it's probable, highly likely that the drug has effect on the, depending on the age, has different effects on the age of the patient. So the important statement here is that before any assessment was made, they assumed that all 3 drugs will be equally likely to be the most effective or least effective treatment. So this is their null hypothesis, that all of the drugs are equally effective. And so their Bayesian analysis then begins with their prior distribution, which they said they assumed that all 3 groups were equal. And so what they're starting with is what's known as a uniform distribution, which is a distribution between 0 and 1. And so it can take on any value between 0 and 1. And then this was updated on the basis of the observed data, whether they were seizure-free after 60 minutes. And so their uniform distribution here is their prior assumption, and that's referred to in Bayesian analysis as a non-informative prior. In other words, if it turned out to be equal, then if we looked at the response rate or the success rate of each group, they would all be equal. And so they're based on the data that they obtain, then they're going to update this prior distribution with the posterior distributions. And so the way that you do this in Bayesians, which actually makes it or emphasizes another point, that Bayesian analysis really only became feasible with the development of the computer. Because what you need to do is you need to do a lot of draws from these distributions to get, from the theoretical distributions to get an idea of what the treatment probabilities look like, or of success for each one. So they're looking here at the probability greater than 0.975. And so, based on our discussion yesterday, you remember the normal distribution. So this would be basically in the classical, or the frequentist, would be analogous to an alpha of 0.025, a one-sided comparison, as opposed to a two-sided comparison of 0.05. So we're at 2.5% of the area under the curve on one side of the distribution. In this case, it'll be the left side of the distribution. And so they just go into how they came up with this, and so they set this up so that only one treatment could be identified as the best in comparison to the other 2. So they ended up with a sample of 720 patients, and to identify the most effective treatment when one group had a true response rate of 65%, but the response rate in the population was only 50%, or in the other two groups. So here is they're telling us what their effect size is here of 15 percentage points, 65 minus 50. And so they're going to report the percentage response in each treatment group with 95% credible intervals. And so now the parallel here in the frequentist is a confidence interval, but in Bayesian statistics, it's referred to as a credible interval. And so even though it sounds like it's kind of the same thing, they have different interpretations. So what did they find, or what they want to show here is that if we represent our red distribution here as the distribution that has a rate of 65%, and the other two distributions have around 50%, or maybe more or less. So our test, basically, when we do the Bayesian statistics, we're going to look at whether only 2.5% of our distribution of success falls within the distributions of the 50%, or the non-success rate. And so this is essentially what we're doing when we do Bayesian statistics, is we're looking at the distributions here, not necessarily at comparing like means, okay, or some particular statistic, although we can do that as well. So this is what they found after going through all of that. Basically, they found that there was no difference in the percentage of patients with seizure cessation among the three drug groups. And so over on the right-hand side here is a picture of their distributions that they got from drawing, I think, what was it, 10,000 samples from their posterior distribution. And so you can see that the distributions of the three groups are pretty much right on top of one another. And when they compute the credible intervals here, you can see that the credible interviews overlap pretty much the same for most parts. So their conclusion is based on their research that they find no difference between the three groups. And so the difference here with the frequentist perspective is that rather than coming up with a p-value that suggests over the probability over infinite random sampling, whether we would get these results or not, what the Bayesian interpretation is that we are 95% certain that there's no difference between these groups. Okay. So in a Bayesian confidence interval, if we talk about a 95% credible interval, what we mean is that there's a 95% probability that the interval includes the population parameter. The frequentist confidence interval means that over repeated sampling, the interval will include the population parameter 95% of the time. Now you say, well, boy, that seems like it's awfully similar, or I don't really understand the difference. And it does, kind of take a while to get sort of the, what the difference is here. but the frequency or classical confidence interval is based on the concept of repeated sampling. So that if you sampled an infinite number of times, then the true population parameter will be included in the interval 95% of the time. From the Bayesian perspective, what's called the credible interval, that's the probability that the population parameter is included in that, or that the true population parameter is included in that interval. Okay, and so in some ways, people sort of like the Bayesian interpretation because that gives you a confidence interval or a statement that you can say that, well, you're 95% certain that based on our study, these are this is the actual probability that we can come up with for rejecting or accepting the null hypothesis. Okay. So the last example I want to give here is using Bayesian sensitivity analysis or probabilistic sensitivity analysis in a cost-effective study. And this is where the Bayesian perspective comes in really handy, or is really nice compared to the classical or the frequentist perspective, because we can set up some really complicated designs from a Bayesian perspective that are almost impossible to duplicate in the frequentist perspective. And the probabilistic sensitive analysis, it really illustrates this. So if you're doing a study where you have fairly simple statistics like comparison between two treatment groups, or comparison between means or proportions, it's just as well to use the frequentist calculations for test statistics and p-values, because it's easier to do, and that's most software is set up to do the frequentist computations. And if you do the Bayesian, do it though from a Bayesian perspective, you usually come out with the same answer or the same conclusion. So if you have a fairly simple design, even though the statistics might be complicated, you're better off just doing it from the frequency perspective. However, if you have a really complicated design, you might want to look at it from a Bayesian perspective. And so this is the case that we have in cost-effective analysis, where we have multiple input variables to estimate multiple parameters. Okay, so and the idea here is that the estimation of the parameters is sensitive to changes in the input variables. And so, for example, you might have say you're in the Bayesian perspective, prior and posterior distributions, you might assume are the same. So like if they're normally distributed or gamma distributed, whatever, they might be the same, but you could have different distributions for other variables. So I'll give an example here of where that comes into play, where not only do we have multiple variables, but the distribution of the variables are not the same. And so in cost-effective analysis, what we want to do is we want to compare the cost of, say, two treatments and look at the effectiveness of those two treatments and determine whether the treatment is what we call cost-effective. That is, even though the cost might be higher in the treatment group than in the placebo group, its effectiveness might outweigh the increased cost. And so what we need to do this is data of set of costs and measures of effectiveness. And typically, the outcomes that we look at are usually like survival or what we term life years gained. And then we can also look at what are called quality adjusted life years. That's basically just taking the life years of the survival and multiplying it by a utility, which is a measure of health status, and it's typically scaled from 0, meaning you died, to 1, where you have perfect health. And so if you multiply this utility by the survival time or the life years you gain from being on the study or being in the treatment, those are then what we call quality adjusted life years. And then, of course, we have the cost of the treatment, which could include procedures, physician costs, medication costs, hospitalization or office visit, lab tests. So there's any number of costs that we can include in our analysis. And so here's an example from a study that we did some time ago where we looked at cardiovascular events. And so I have just a couple of examples here, and this is broken down by age groups. And so what we have here is like the mean cost for a fatal cardiovascular event in the 45 to 64 age group is close to $19,000. It's a little bit less for the group 65 to 84, and then even less for the elderly patients. And then the same thing here for the cost of a non-fatal myocardial infarction, broken down by age. And so we're going to use our mean age here as the cost. If a patient experiences a particular event here, we're going to use this particular cost. Typically, the costs are distributed as a gamma distribution. And basically what a gamma distribution is a right skewed distribution. So anytime you do a plot of the distribution of costs, it's going to look like this, where you have most of the costs are down at the lower end, but you always have a few costs that are really large. And so you get this kind of distribution that's right skewed. That is, it's skewed to the right side of the distribution here. So obviously this is not a normally distributed variable. And then we have to have, in addition, if we're going to do quality adjusted life years, we have to have some utility values. And so we get this from published studies. So what this means is that if you have a history of angina, then whatever your life years was, whatever your survival time was, we're going to multiply that by 0.9. So it's decreased a bit from what it would normally be if you had no history of a cardiovascular disease. And the same thing if you had a history of stroke, then we're going to multiply your life years times 0.88. And so this is would be applied to your history, your cardiovascular history. If during the study you experienced, say, an MI or stroke, or you had a coronary artery bypass graft or a PCI, or if you had angina, then we're going to subtract this from your quality adjusted life years. And so this is usually looked at as a beta distribution, which again is a distribution that goes from -1 to +1. But as it may be, this is all predetermined before we start the study. So, and as I say, we get this information usually from different studies or studies that have been previously been done, or someone based on data has come up with these values for utility. Okay, and then so the main statistic that we're interested in cost effectiveness studies is what's called the incremental cost effectiveness ratio, or the ICER. And that's basically the difference in cost between the two treatment groups divided by the difference in efficacy between the two groups. And so what this gives us, say if this ratio turned out to be $50,000, what that means then is that for every $50,000 we spend on healthcare, we're going to gain 1 quality adjusted life year. And so that's then based on this, although it's obviously an arbitrary decision, what's cost effective and what's not cost effective comes down to how much you're willing to spend to say prevent 1 case of a heart attack or 1 case of a stroke. And so this is usually displayed in the cost effectiveness planes, which shows the different possibilities that we can come up with. So we may have in quadrant 1 over here, we have increased cost, but we also have increased effectiveness. And so this is called the cost effective quadrant. We might, in quadrant 2, we actually have the treatment is effective, but we have less, it's cheaper, it's less cost. So that's actually sort of the best outcome possible. And then over here, we have kind of sort of a no-win situation. The cost is less, but so is the effectiveness. That may or may not be relevant. And then we have in quadrant 4, sort of our worst case scenario where the cost is higher, but the effectiveness is lower. And so the way that we do this, and this is where the idea of the Bayesian analysis comes in, that we can do in a fairly complicated design or study here. And so I've set up an example here, quite a simplistic example, because usually they're more complicated than this. But so over on the left here, I have the cost of a fatal cardiovascular event, the cost of a non-fatal MI, the cost of a non-fatal stroke, and then the cost of taking atorvastatin, or it could be any statin. And then over here, I have my distributions for a history, which is where we get our quality, our utility values, and then multiply that by our survival or our life years gained. And so what we can do is that we can draw from these different distributions simultaneously. And so I've given an example here. Say we have a patient that's had a stroke. We have the cost of that, and they're taking atorvastatin. So we have the cost of that goes into our calculation, and they have a history of angina. So that would go into the calculation here. And so we do this a large number of times. So this might represent one of our random draws out of 100,000 that we're going to do. And so what we come up with then is our incremental cost effectiveness ratio, our difference in cost divided by the difference in qualities between the treatment groups. And we've done this 100,000 times to get a distribution. And so what this looks like when we plot this, on the horizontal axis, we have the mean effective difference in this case, quality of life. And on the vertical axis, the mean difference in cost. And so what you can see here is all of the little dots here are the thousands of replications that we made. The large dot in the center here, this is the computed incremental cost effectiveness ratio. And then the confidence bands here indicate the inner band being the, I believe this is the 90 percentile confidence band. So in other words, 90% of our random draws fall in here. The next one is the 95% confidence band, and then out here is the 90% confidence band. No, I've got that backwards. It's the other way around. This is our 90th, the 95th, and then the 99th. So in the widest band here, we have 99% of all of our replicates that we've made. So this gives you an idea of a more complex kind of research that we can do using Bayesian statistics rather than the frequentist statistics. Okay, so to summarize then, from our frequentist position, that's based on repeated sampling of data from a population. And the confidence interval means that over repeated sampling, the interval will include the population parameter some percentage of the time. Usually we look at 95% or 99% confidence intervals. The Bayesian analysis begins with making some assumption about the prior distribution of our statistic. We collect the data and then we revise our prior assumption based on the data, and that is what we call our posterior distribution or our posterior probability. And so in Bayesian statistics, the interval called a credible interval is just the probability that the interval includes the population parameter. Okay, this is based, the Bayesian is based on assumed distributions or assumed theoretical distributions. Whereas in the frequentist, it's based on the data, sampling from the actual data. But in Bayesian statistics, we're sampling from theoretical distributions. And so that's one of the criticisms of Bayesian statistics is that you don't know what you're making some assumption here about the prior distribution. But there's a whole literature on the implications of making certain decisions about what the prior is. Okay, so as I mentioned, if you have fairly simple analyses, you're better off just using the frequentist methods. But if you have a really complex kind of study where you have multiple parameters, multiple distributions that you want to draw from, then the Bayesian perspective is probably better to use. And then one thing that you do in Bayesian simulation is that you have what's called a burn-in period. You do your simulations or your drawing from your samples a large number of times, and then after that burn-in period, you use the last set of results to report. Okay, I see I've kind of gone over time again. There's a few references here. And then I wanted to kind of give you an assignment here that's not, I don't think William has this set up, but for an exercise to program in Python, use a diagnostic test that we know has a sensitivity of 0.82 and a specificity of 0.78. And then so what you can do is then you calculate the predictive values, both the positive and negative, for different disease prevalences. And so what I've indicated here is look at prevalences from 5% to 75% in increments of 0.05. So you would get a table, come up with a table that looks like like this, where you have each of the prevalences and then the positive and negative predictive values for each prevalence. And so the formulas that were on slide 18, those would be what you would use to calculate the predictive values, and then to program that into Python. I'm not sure if Python has set up algorithms or routines to calculate predictive values given sensitivity and specificity, but if they don't, you can easily, use those formulas to program that. And then obviously what this is going to require you to do is to loop over several prevalences or a number of prevalences from 5% to 75% and come up, print out a table that looks like this. So I'll stop there. Thank you for your time, and I'll turn it back over to William if he's there.
Yes.
Okay.
So yeah, thank you, Paul. Thank you so much. And so, John, we are at a point where we would like to take a break, or what was the plan? Okay, so I think in the absence of John, I think let's take about maybe a 10 minutes break. And as we do the break, please try and make sure you have your Python environment open up. We haven't updated GitHub, so whatever files you have will be fine. And then we'll probably just continue with what we did. As Paul was going through the material, I was also doing some coding here. So I'll make this code available with a confusion metric. But what we will do, the plan will be to get students to go through what was given, and then once we come back, I'll continue with where we left off. So please take a 10 minutes break, and we'll be back at 12:20. Is John back? Okay, yeah, so let's do that. Let's take a 10 minutes break. And then in the 10 minutes break, please make sure your Python is set up. Otherwise, you'll not benefit from the class. Okay, thanks a lot. See you at 12:20. 20, we have a minute. Okay, so we're going to start now. Let me share my screen. I'm hoping to start sharing this one. Okay, it says I'm sharing. So which of the screens do you see? You see the one with the blue population?
Yes.
Yes.
Oh, good. Okay, that's good. Because it's not giving me that red thing. Normally I see a red banner. Okay, so let's so definitely we want you to work in Jupyter. Otherwise, you cannot open the Jupyter notebook. It's going to be if you open just a Python editor, you're going to be in trouble. So if you don't have your Jupyter is not working, we have Codio as a backup. So use Codio, and you can send Nana or put something in the chat. Okay, so primarily what it is once you go to Codio, you would have we're still working with the student file. Okay, so just use a student file. Okay, so your student file. Hopefully, when you went home, you were able to go through. Yesterday, we rushed through some of these materials, but hopefully you went through it. And we're going to continue from where we left off. We're going to use Paul's PowerPoint as a reference. Okay, so let me get the PowerPoint, and then any new materials that we add, we're going to make that available as part of the whatever will be posted. Okay, so if you open Paul's material, then we are at a point. Yesterday, if you recall, we saw this data set. Okay, so we saw this data set and we were playing with it. And so we're going to try and continue and see what improvements we were able to make after going back home and looking at it. Okay, so I'm going to work on the instructor file. You look at it and run it by your student file and see if stop me where you it's not clear. Okay, so we did the installation. In your file, you're going to see something like an exit here. The exit means that if you're using Codio, this installation has already been done for you. So there's no need to run these pip installs. And that's why I have this exit here, because the install takes time. But if this is your first time, then you want to comment this. And this means that you're not running Python, you are running the shell. Okay, so you're running bash. So we're doing a pip install and all that. This is equivalent to someone saying exclamation pip install pandas, say. Okay, this is very similar to that. So this guy here is very similar to this guy here. Okay, so I could have done that. Now the bash helps so that I don't keep doing, so it says the whole thing, everything in this cell is going to be run in the bash mode. So these two things here are equal. This is equal to that. So people. Exclamation is very, this is a pseudo. Okay, but outside the bash. Okay, so you do this if you were using a Python cell like that, then you have to escape to shell. The brand means escape to shell. The alternative is to say run everything in the shell and then just do sudo, 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 sudo. Okay, so that's primarily what this is doing here. This is running this in inside the Python, and this is interpreted as a shell. Okay, how do I know that? Because if I put a stop here and I run, I'm going to get that echo being echoed out. Okay, like that. Okay, cool. So we've done that. Make sure you have your pandas and the NumPy, because those are the two data types that you'll be playing with. For heavy data manipulation, the list and the vectors won't work very well, but these arrays and the data frames will be the best way to go. Okay, so we saw this file, so there's no, we don't have to go over it. We just load the file. You can either load it by manually loading it or loading it from an external file. Okay, and you see these things, don't worry about them, we'll talk about them. You see how, once you start looking at the data, you see how we want to reshape. Okay, but we'll talk about it. So yesterday we were playing with just the base NumPy doing the sum, and then computing the mean using the sum and divided by the length. Okay. Alternatively, we could use the NumPy method mean, and then so we went through this. Were there any difficulties when you went back home? Were there any difficulties as far as the first portion goes, please? Okay, I think the only thing I did differently here was that, if you recall, we were struggling with the sum. Okay, so in Python, the data type is always what can get you into trouble. As you work with your data set, always do a type. If you recall, Professor Musa showed us how to do a type. So see what data type you are working with. Always, always, always do that. Okay, so if you know the data type you're working with, then you know what library to use and what methods to use. This is an array. So if this is an array, I'm not going to use anything in pandas. I'm going to have to use NumPy. Okay, because to use pandas, I have to convert it to a data frame. Okay, so take note of that. I always do this, and that's what got me into trouble. Recall yesterday we were struggling with the sum coming in front, but this time here we're using a NumPy data type, and NumPy data type has a method called sum. So you can just do the np.sum. Okay, so that's your data type of sum, and get that. Okay, so now yesterday what I was trying to do was that I said, okay, you know what? Why was I struggling? Is it possible to do this on the fly instead of just playing around with the numbers? And so I went back and actually worked with that. Okay, and I'll show you what I mean by work with that. So you see that instead of combining the whole thing and getting stuck with it, it's always good to do things in parts. Okay, so I take my the part that I feel comfortable working with, store it, observe the type. If possible, take a look at what is in there. And then I can then go ahead and this time, you see now, I have an array now. So now, or I have an array now. Yeah, could have been a list. I have an array now. So now I can use the sum on the array. And now I got it to work. Okay, yesterday, if you recall, we were struggling with this, whether the sum should be a method or it should be just a function. Okay, and then this looks much more easier to the statistician than putting everything in here, which is what a Python programmer would do. And the reason is that Python programmers are hardcore programmers, and they want to have things in a more concise form. And that's why they have things like lambda functions and things like that. But in my case, I feel comfortable looking at this. It makes more sense to me that if I take things in steps, then I can easily use functions that I'm aware of and get the values out like that. Okay, so this looks almost close to what we have in here with some rounding taking place. Okay, so that's the first part. We're not going to waste any more time. Alternatively, you can use the stats library. And if you use the stats library, then you're all done. You just call the mean on the data type. You call the variance on the data type. You call the standard deviation on data. 3 lines of code versus the whole frustration upstairs. And that is what this class is about, that there are functions and methods and libraries that you can utilize. Just getting to know that they exist makes life easy. Okay, so 3 lines of code, and I got output that looks like what is in there. Okay, any question, please? Okay, and the part that we're saying try using the function is the same thing. The function, you take your time and break it down into parts, okay? So we know we want the length. To get a standard deviation, you have to get the mean deviation or the square of the mean deviations and divide by the n, and then take the square root. So you do it in parts, and then you return, and there's a cool thing with Python. You can return more than one item. Okay, you just say return A, B, C, D, and it will return all those. And so you have to hold on to them. Okay, so once I run this, the result is going to have a result dot, the mean part of the result, the variance, and the standard deviation. So I will then get in and print them in here. Okay, so you run that, and this is primarily just beautifying it. If you don't want to do it that way, all you do is you come down here and you just display what the result is, or you can do a result of columns or just do results, and you get the same output, the 3 outputs. You did write your function, so you know what comes after what. Okay, so you can do something like this, and this is also one cool thing with Python. You can actually do that, and now you can just print the standard deviation. Okay, like that, and you have it. Yeah, so that's a cool thing with Python. I know what it's returning, and so I can just hold on to it. If you don't know what is returned, if you didn't write a function, then you can do something like a question mark on that, and it's going to tell you it is a function. There's no docstring. There's a bad program on that. Hey, William is a bad program. There should have been a docstring, but we'll do it in the TA session. Basically, you put a documentation in there to indicate what the function takes. Let's say if you know mp.mean, that's always what I do. If I don't know how to do the docstring, you do something like I think mp.sum. There we go. So there's a docstring. You see what the docstring does? The docstring tells you what the function does. Okay. So the first time it did it, it does that it went into our output. Okay. So what the function does, what it returns, so that it makes life easy for anyone using it. Okay. So this part is elementary. I'm not going to waste time just to get us all in good shape. And it's always good in data analysis. What you do is you visualize the data. Visualization is always part of the data, right? You look at what the data looks like, what the data is telling you, and then it helps you drive your analysis. Okay, so here from our previous lecture, you just call your matplotlib and you pass it the variable. Okay, so if I do that, then I get now. Okay, cool. And then there's another form of visualization using the Seaborn. And so just go back to your notes with Dr. Musa. And all we are interested in is we want to use Seaborn on our data set. That's all we are interested in. The rest of the notes from Dr. Musa apply, and you get a shape that looks like that. This is more like a density plot, overlaying a density plot on the histogram. And that's what this is. It's a density plot. Okay, it gives you the distribution. And this, you remember one of the slides Professor Paul showed where he's saying you doing cost analysis is always skewed to the left. You'll see something like that. Okay, so at this point, then you are done. Then you are really into the flow. Now we do the inference. With the inference, this takes a little bit of understanding. So I'm going to take time and break it down. So here, what we're doing is that we're taking samples. Okay, from the slide, slide 16. We want to estimate the population mean, and so we take samples from that data set that we have. Take samples of 5. Each time we take a sample, we compute a mean. Take a sample, compute a mean. Take a sample, compute a mean. When you compute the mean of the means, it should come close to the population mean, and this is the basic stats 101. I mean, this is the sample mean for large samples comes close to the population mean. And then why would you use a sample mean? Use a sample mean because you may not have access to the population parameter. I mean, that population estimate. So use a sample mean to estimate the population. And one way of doing that is to use bootstrap. Okay, you take sampling with replacement because you don't have enough data. So if you take and you don't replace, then you run out of data. So bootstrap means take a sample, put it back, shovel it, take another sample, put it back, shovel it, take another sample. Okay, so that's what we're going to do in here. Okay, so we have a sample. Okay, we have a sample. This is our sample, and we're drawing a random sample of size 2 from that data. We show this. If we run this and we don't do the seed, then each time we're going to get a different value. Okay. And so if we increase our size to like 6, then we're going to get a different value. And then we take a mean, store, mean, store, mean, store. When you compute the mean of the means, you get, or even not just the mean, you can do the standard deviation. Any statistic you want to do on the population, you can do on the sample, and you get an unbiased estimate, as they call it. Okay, cool. So we went through this. This is just showing you how to run the random sample. If you haven't seen that before, just open the cell and then just put it in random.sample, and it will tell you how to do that. Okay, so random.sample should have put it in the output. Oh, I don't know why it didn't do that. Okay, but it should give you an output. It should give you what random sample does. I think it did, but I may have closed my. There we go. Yeah. Okay, so depending on the editor you're using, it will pop up, and you'll be able to see it. In my case, I was hiding. So this is saying that you're taking K sample, so you have a population and the sample size that you want, and if you run it, and if it's still not clear, if you scroll down, you'll see an example. And so normally what I do, I just take this and just run it, okay, and you should have gotten an output. I don't know why this didn't. Well, that means they made a mistake in there, or you have to turn this into a real array. So mp.arrange, I think like that, and then it's not an MP. Okay, anyway, but we have a way of doing that. We have our data, we take a sample and get an output. Okay, and to get rid of this, we just run it. Okay, so we know how to do this. Okay, and we show that you can take a sample, look at the index of the sample, and use the index to reference the data that you are interested in. So I take a sample using the index, right? So if I take this and run this, okay, here, I'm able to get what index is. Okay, so index is just going to give me a bunch of indexes. The length of this data set better be more than what the index indicated. Okay, so this length should be more than what the index. Any of these terms should be less than or equal to this number here. Okay, that means you are within your range. Now, once you have the index, then you can say, give me the data that corresponds to that index. That's all we're doing. We take this, we take dBP and say, give me BP, give me the first element of the list. You can say, give me the first and the second element of the list. Okay, so you can do that. 4 and 5, and sorry, this has to be a list. Okay, so give me that, and you get the data that corresponds. So that has been extended into this. That I have my index, then I can run my index on the data, and I'll be able to then get the index and the data that corresponds to the index. So these are the index, and there's the data. Let's check. You take 102, and you run the dBP on that. You should get 91, which is that. Okay, so this just steps, and that you see how I did it. Take your steps before you do the big thing. If you do the big thing, it's going to bite you, unless you are very, very comfortable, like Professor Musa or any of those programmers. Take baby steps. Then once you take baby steps, you can go back and clean it up. Okay, so I've taken baby steps. I've seen what I want. So now I can put it in a nice programming form that all I'm doing is I am taking a sample of size, let's say 12, say, okay? So I'm taking 12, a list of size 5, but 12 of those lists, and I'm printing them. Okay, so if you run this, you're going to get a list, okay, of size 5, but 12 of those. Okay, so if I can do 12, I can do any number at all. I can do 25, just like Paul did. And I like actually parameterizing my code. That way I don't have to come in here and change. So if the main code works, then all you do is just change the parameter. And now I can go to 24. And I have 24 samples. And I have 25 samples. Okay. So this leads us to Paul's next thing, where he defined. So this is, and the slide numbers are always indicated here. Slide 17. So if we bring slide 17 in here and go down, okay, so we're going to do this, okay? So you're taking a sample of size 5, take the mean, 5, take the mean, 5, take the mean. You do that a number of times. And then once you take the mean of this means, you get a value that is an unbiased estimate of the population mean. Okay, that's all we're doing in here. Okay. And can I get, oh, please, can I get this one? Okay, yeah, no problem. If there are any questions, please just talk and I'll stop and go right. So this is assuming that you've gone through the notes, and so I'm just speeding up. Okay, so here, I know how to take a sample of 24. I should be able to take a sample of 25. The only thing then I have to do then is that I should then compute the mean of that list that I created. And we've done this before. So if I just come in here and I take this number, right, this list, and I put it in here, and I say the mean of this, so np.mean, and be careful of your data type. Okay, so np.mean of this. If you get an error, then you have to go back and look at the data very well. That means that you are using something else instead of mean. So if I'm able to take np mean of this, then I can take np mean of that, and I can take np mean of this. Assuming I stored this, okay, assuming I stored this number as a sample, okay, so let's say I stored this number here and call it, let's say, my sample, okay, then I can just get a mean of my sample. Okay, so my sample. That's why I like the other code automated, code completion things. So like that, and I get the same value. Okay, do that, it's gone. I take it out and it comes back. Okay, cool. So if I can do this, then I'm done reproducing this, because then all I have to do is to just hold on to the mean, okay, which is here, which I've really encoded it into my output, into my print, which is not a good idea. But I've put it in there. As you go back home, you can make it nice. You can actually put something in here like this. You can move this thing out, Control C, put it somewhere here, and call it, let's say, M, say, okay, M equal that, in which case then you can just print your M instead of putting it as part of the print statement, because it can really get you. Okay, so I put this as M. Okay, and then I get the same output like that. Okay, so break your things into steps, comment your code, so that when there's a problem, you can easily see where you have a problem. But here I can clearly see that I take a sample, which is basically what I'm doing in here, just taking a sample. I come down, I take the mean, which is what I did in here, and then I print the sample and the mean. And this, you learn this as you see more of the print statements. Okay, you learn as you see more of the print statement. And then I make it nice by just beautifying it. Okay, cool. I think Professor Musa will look at it and say, hey guys, you know what, I taught you data frame. What are you doing all this look for? What are you doing all this look for? Now, the reason we're doing this is once you know how to do this, then you can easily do it in a data frame. Okay, so I have a prototype. So now I can do it in the data frame and I can do it much, much cleaner. Okay, the cool thing with the data frame here is that you can manipulate the data frame, because think of a data frame as an Excel file. If I have an Excel file, then I can just say, hey, give me the mean of column 1, give me the mean of column 2, give me the standard deviation of, and that is what we are doing in here. Once I'm able to create my data frame, okay, so let's try that. I take my data frame. So now I can print my data frame and look at how it looks like. So let's say, let's go here and put a print in here. Print DF, okay? And let's primarily see how this works. And I always like, in case you're doing it and you don't think you're sure, just open up a cell and just print. That's the data frame, okay? Okay, so that data frame that I created, in fact, I think I did a bad thing here. Let's take this. Okay, so what I did here is I got this. Okay, let's run it. So now I have this rows is primarily doing an inline expansion, okay, a for loop. Okay, so I'm running a for loop on the range of number of samples, and I'm then building a random sample out of that and storing as rows. So if I print rows, let's see how rows will look like. Because once I have rows, then I can easily turn rows into a data frame. So that's rows. So this is row 1, row 2, row 3, row 4, row 5. And always, always, always try and see the type. Okay, so print the type. The type has to be your bread and butter. If you know the type, it makes life much, much easier. So the type of rows is a list. Okay, the type of row is a list. Okay, and so if it's a list, then I'm home free, because with a data frame, you can either concatenate series into a data frame or a list into a data frame. So the list says something like this. If you go back to your notes, you see that a list will be something like my list, okay, equal, and then you do something like A equal A1, okay, and then B, okay, like that, to a name and a value, key value, okay. And so if you print this, my list, then get that. To change it into a data frame is very easy. You just stick this method in front of it, Control V, and now I have a data frame. And the cool thing with the data frame, oh, sorry, data frame, sorry, I may have done something wrong there, but you go back and look at it. Go back and look at it. I think I may have done something wrong in there. I should have done that. Maybe I didn't include the column. Anyway, I don't want to waste time. So I have a list. I've got a list called rows. I can then turn the list into a data frame. Okay, and to turn the list into a data frame, I just say the columns are A, B, C, D. okay, which are the 5 columns. And from there, I get my data frame. Okay, now I have a data frame. So now the sky is the limit. Okay, the sky is the limit. Let's go back here so we have access to this. So I have a data frame. I print the data frame. And the reason I'm re-indexing is that if you have a data frame and you don't re-index, I mean, I wanted my output to look almost close to what Paul had. Okay, Paul has this index starting from, if you look at the main one, it's starting from like 0. I mean, like 1. Okay, 1, 2, 3, 4, 5, something like that. So I wanted mine to also start from 1, 2, 3, 4, 5. The ones, it makes life easy if I'm not a real Python program. Okay, so that's why I'm doing this. I'm doing the reset. Okay, I'm resetting the index so that I'll get 1, 2, 3, 4, 5. So this is saying for my sample one, I get a mean, and you see this looks very, very clean compared to what we did with the loop. Okay, so I have a row and I take the mean of the row, and that's what this guy is doing. Axis 1, that's the row. Okay, sorry, that's a column. I'm taking the column mean. A row mean will be axis 0. Okay, and I didn't want the decimal because I want my values to look very similar to what Paul had. So that was the reason why I put that integer thing there. So let me block this. You see, you're getting this value, but Paul's numbers were integer, right? The means were all integer values. So I just out of a little Google here and there, I get integer, and then I display that. So now I have something that the sky now is the limit. I can tag on the standard deviation, I can tag on the confidence interval, I can tag on a whole lot of other things because now I have a data frame. Okay. We look at slide 19, and Paul computed other things, the standard error of the mean. And the standard error of the mean, if you look at slide 19, is just take the standard deviation multiplied by 1 over the square root of n. And then that's also, you look at slide 19 is there. So we take an example, which is what Paul gave us. We have two samples. We take the mean. We know how to take the sample mean. That's no problem. Okay. We want the n, so we take the length of, now the samples have the same length. So taking the length of sample 1 is the same as taking the length of sample 2. It won't cost anything, or even you can hard code it as being 5, and that'll be fine. The computation is done here, okay? And then the question is, how do you want to display your result? You can display your result nicely like that. If this is intimidating, just print them out, okay? So I'll just print them out like that, and that's the value, okay? Just print them out, and this is what we got in there. Okay, that means if I change the formatting, then I should get more decimal places in here. And the same thing here. If I make this 3, then I get that. Okay, and that's why I like the print. The print allows me to control my output. Okay, if you don't use the print, then you're going to get a whole lot of, I think it's about 15 decimal places. Okay, sure. So now once you have that, you go back to the notes, go to slide 20. And you know how to compute the standard error of the mean. So then you can actually get the upper and the lower bounds by just plugging it in the formula. And there are ways to do that more efficiently, but I like taking baby steps. So I compute my lower bound for sample 1, upper bound for sample 2, lower bound, upper bound, and print them. And the print, I've taken time. Right? When I was learning Python, the print was the first thing. I don't know, maybe because of my CSI background, but I like seeing things so that I don't have to explain it to the user. You know? So when the user sees this, the code is more comprehensible. Okay, so I like beautifying my output, and that's why one thing I also like data frames, because it allows you to label your columns nicely, and the rows are given for free, and things look nice. Okay, so up to this point, are there any questions? Were there any struggles? Are there any questions? Are we going too fast? Are we going too slow? 54. Okay, so no questions. We keep going on. Alternatively, you could use the stats. The SciPy has a way of computing this, okay? And the cool thing with knowing what each of those libraries do is that they make your work easy and they make your coding clean. So you can see clearly here that me using NumPy, I'm able to compute the standard error of the mean. It's given in the SciPy packet, in the start module that exists in the SciPy packet. How do I know about that? I know SciPy is for scientific computing, NumPy for numeric computing. So for scientific type of statistics, it's going to be there. Or just Google it. You just say standard error of mean, Python, how to compute, and you get that. So once you have a package that computes the standard error of the mean, you have another package or library that computes the mean, then, and you have another package that computes other measures, then you can just concatenate all of them together, okay? And you get a nice, a nice concise code. So here, with a few lines of code and a simple definition of a function, I'm able to reuse a function on the two samples, and I get values that I'm able to then plot. Then print out. Now, if you don't know the dimension of each of these, I always print them first. Okay, so when I used it, the print didn't just come automatically. I displayed it to see that I have three values. So I have a value, the lower bound, and the upper bound, and that's how I use it to display this. Okay, so with that, you have an output that looks very, very close to what Paul has on slide 20. You got a sample, you got a mean, okay? You got a standard error of the mean, okay, which is 3 right there. And then you got the upper and the lower bound. And so if you match this to that, you get something that looks like that, okay? So at this point, hopefully there are no questions. We've been able to replicate this, okay? And so this will come handy when you look at the assignment Paul gave in the last lecture. If these things will come handy, that don't look at the assignment in its entirety, break it down into smaller chunks, and then eventually tie everything together. And as you see this, I'm breaking things into smaller chunks, and then I'm going to tie it together. So now I can do 2, then I can go ahead and do the rest, okay? So now doing the rest becomes a trivial task. For so long as I know the formula, the sky is the limit, okay? Sure. So and that's the case where here I'm increasing it from 25 to, from 9 to 25. And then I'll be able to display that. Okay, so let's run that and we'll get something that looks like what Paul had. I like the data frame concept because the data frame, I don't have to indicate what is in the data frame to be printed. I just say, show me what is in there. The column names are given and the row names are also given and the data looks nice. Okay, cool. So at this point, I think we are doing fine. We have exactly what Paul has. So the idea here is that we take the mean. So if we do a mean on this column, then we're going to get the population estimate. Okay, and this is the standard error of the mean, and that will give you the standard error of the mean for the population as well. Okay, cool. So that takes us through that, and so we'll keep going. This is just try this on your own type thing. Okay, so now we are done with the part that's doing the sampling. We go to the part that's doing the hypothesis testing. In here, you look at the formula given. For a t-test, there's a formula. Once you can understand the formula, implemented in Python is really, really very trivial. Okay, just take it baby steps, numerator, denominator, even the denominator, break it down so that you can see where your error is coming from. And then once you get it, then you can use a package to do it in a nicer way. Yeah, luckily, we've been giving values here. So if we go wrong, we'll be able to tell. So we are back on slide 34. For those who have single screens, slide 34 is this portion of it here. Okay, so we're going to go ahead and compute the p-value, and then we're going to go ahead and see how other statistics are being computed for a categorical data. Okay, so we're going to do this proportion, differences in proportion, and hopefully we'll get this confusion matrix here. Okay, so let's do that. The main things that you want are, you want a way to hold on to your data. To hold on to your data, we're going to hold it on using the list. Okay, we know how to handle this before. Hold on to a list. So we have the control and the treatment. We want to turn it. I like working with data frames, and the reason is that they are for heavy lifting. Okay, so they're going to prepare grounds for other things to come. So I convert this to just a column in the data frame called a series. So I have one series, another series. Okay, and now I have a frame which is just a dictionary, and I can turn that dictionary into a data frame. I don't know why when we did it before it didn't work, but this is how I create a data frame. You have a dictionary, and the dictionary primarily looks something like this. So do a plus, stick it here, okay? And so if I do a frame, you're going to get something like that. You see, it's a column. You see that frame, that's it. So one and another column. So you can tag them on together in a data frame, and the data will look nice like that. Okay, so I have a treatment and a control. And always in my machine learning class, any data that is thrown at you, look at it, visualize it. Okay, because the numbers, after 3, 4, you forget. You forget whether it's, you really forget. But once you have a visual, then you know here, I can see clearly that consistently the control, there are more control samples on the average compared to the treatment sample. Is that important? Maybe. If I want to make sure that I'm getting fairly equal amount of sample, then this is a red flag. Okay, but just plot your data before you do anything at all. So visualize your data. Alternatively, you could use a Seaborn, but just any form of visualization would help. Okay, and if I do my Seaborn, I keep getting these warning messages, but I do my Seaborn, I can see the distribution of the treatment and the control groups. Obviously, the two groups are different. Two groups are different. One seems to be slightly skewed to the left, and the other seems to be slightly skewed to the right. Okay, so if you think this is good for your experiment, then that's fine. If not, then you have to go back and revisit the data. But these are the tools that you use. Okay, so now let's look at we're computing the 95% two-tailed z-test for the differences in proportion. Okay, so how do we do that? And SciPy comes very handy. Okay, SciPy has a way for you to compute that, and the method's name is t-test index. Okay, so you take the t-test index, you give your treatment and your control, and it returns the test statistic and the p-value. It's really very cool. If you want to implement this by hand, it's going to take you time. You have to go through Paul's notes and implement it one at a time. So as a way of trying things on your own, you can do that, and then you verify using this test. But if you recall, Paul had a negative 1.41412 with a p-value of 1.9. So this convinces me that this trend here is doing the right thing. If you look on slide, the slide that comes with that, I very much remember this negative 1.4 value in here. But this is what you do. You just call the method, give the two lists, or the two lists that contains your numeric data, and then you get the values, the p-values spit it out. Okay, and how do I know how to use this? You Google or you use the question mark. Okay, so once you use the question mark, you're going to get an output and it tells you what it does. Okay, so it's going to tell you that it's a t-test, 2 independent sample scores. Okay, so there are a lot of methods that are available for free. You just have to know they exist. Okay, so now you can compute the t-test. So now you can state your null and your hypothesis and decide whether to reject or fail to reject, whether you reject or fail to reject H0. My stars class said you never accept the null hypothesis. You reject or fail to reject. Okay, so that's okay. And then your conclusion comes, which is what Paul stated yesterday, based on the p-value and the test statistic, primarily a p-value. Assuming we stated that we tested at the 5%, then this is really greater than the 5%. Okay, so we also have a test for proportion using chi-squared, and the main thing is to know how to state it. Okay, so if you look at slide 39, Paul gave us this, okay, the standard error and the z, and so we're going to implement that. And he's given us steps how to arrive at the answer, okay? And so we're going to implement this. How do you do this in Python? It's the same thing here. You see the data, 84, 1, 84, 72, 202. You have to know how to get the data in Python. You need a data in memory. You need a data in memory to be able to do anything. Once the data is in memory, then it's a piece of cake. See this? So this comes from the stars model, library. It gives you the proportion z-test for free. So once I run this, I'm going to get the statistic, the test statistic, and the p-value. Okay, so run that, and you get a value similar to what Paul got. Okay, and then based on this, 5%. If you start at 5%, then you have to state whether to reject or fail to reject A0. Okay, and Paul gave us something similar to this as well, where this looks like a confusion matrix, right? So, and he gave us ways to actually compute this. So then the question is, how do you hold on to this data? How do you get this data in memory? Okay, so the formula is given. If I'm able to get the data in memory, then the formula is then the rest is just trivial. Okay, so the formula is given, and you painstakingly implement what Paul has implemented. So, but for the start, what I did was I just hard coded the values to see if I'll get a value that Paul had. And once I went through it, so these are just numerically coded values. The E1, E2, E3, I just took it and just coded it in there. Now, once I have those E values, then I should be able to compute my chi-square. Okay, and if we go up somewhere, I think Paul had it in one of the slides. This was the value. So the question then is how do you do it in a more efficient way without hard coding like I did? Okay, so I have an example here where I've got a confusion matrix that I've created in a table form, and I'm going to try and compute the row total, the column total, and the total, the sum of all the total. Okay, and then display them. Okay, so once I run that, okay, so nothing here. In fact, the only thing I'm doing here is how to get the data. How to get the data. And the square brackets, if you're a beginner or you haven't practiced Python very well, the square brackets are going to get you. Okay, so the square bracket that indicates that we have a list and we have a list. Okay, so we have a list, 2 elements in it, another list with 2 elements in it, and we want to turn it into an array. Okay, so if we take this and put it in here, then you're going to get something that looks like that. So always look at the data before you jump. Otherwise, things will be mixed up. What you think you see is not what, in general, it's not what how Python takes it. Okay, so once you have the data, then you can compute the total, the mean. Remember, the mean can be computed indicating the axis. Okay, so axis 0 means I'm computing the row total, and the axis 1 means I'm computing the column total. So now once I have the row total and the column total, then I can also compute everything. Okay, the sum of everything in that array constitutes the row total and the column total sum together. Okay, so I have this, and I got something that looks like this, which looks similar to what Paul had. So with this, then just take your time, put that target close to your E1, E2, E3, E4, and then the formula is already there. So then just plug it in and the output will come. The first time you may not get it right, but if you break your work out, put them in cells, then the output will come. It took me like 2 iterations to get it right. And so just take your time and go through it baby steps. And then once it works, then you can turn it into a function or make it more efficient if you want. But at least you have a prototype you can rely on. Okay, so at this point, do we have any problem? So this is the hand way of computing the chi-square value and the p-value by hand, as Paul did it. Okay, as Paul did it using this. How to compute a chi-square value and the p-value. The statistics behind that, rewatch the video if it's gone. I will rewatch the video over and over again just to have it sink in here. Okay, but once you give me the formula, which is what this segment is for, assuming that you have the basics, assuming that you're given all the formula and the data, how do you use Python to make to move it on instead of using Excel or instead of using SAS? That's what this class is for. Okay, so given what we've been given and the statistics background that we've been given, how do you turn that into a code? And that's what we're doing in here. Any questions, please? So it's 1:12. We have a little bit to go, and then so that we'll just keep going. Okay, so that took us through here, and I've given you a whole bunch of references. And the way this is done is it's been broken into segments. Okay, it's been broken into segments. So one segment does the inference, and at the end of it, it tells you that you're done. So you can actually work on it, take a break, work on it tomorrow, take a break, work on it. Okay, so do that. And the references are with respect to that specific one. Okay, so this talks about how to draw a sample. If you open this link, you'll see a Python native how to draw a sample. So this is right on the fly with code as well. Okay, so that brings us to the next one, which is regression. I'm sure there was I've forgotten the student's name. He was interested in how to fit regression. So this will be very interesting to that student. Okay, then this is slide 51. Again, just to make things easy when you go back, just go down to slide 51 here. This is what we're doing. You'll be given the data, and this data is actually on the second sheet of the data set that was provided. So this data set, and that was the reason why when we were reading, we said read sheet 1, and then you're going to read sheet 2. Okay, so now we're going to read the second sheet from this data set, and the data is data.xls. Okay, sure. So let's go back and look at it. So what we're doing is we have this in our minds. We have the data. We fit the data just by looking at the points and fitting them. And then Paul showed us how this fitting fits into the arriving at the equation of the line of best fit and the I think there's a correlation coefficient, something like that. Yeah. So the line of best fit and whether the thing is positively, X is positively, age is positively related to Y, to, I don't know what the other variable is. But anyway, Paul is taking us through the steps of how to do it in a visual way with the formulas in there to indicate how they relate to the point and the line that is drawn. Okay, so there's the correlation coefficient, which is always, it has a magnitude and sign. It's positive 0.8, so it tells you that there's a strong relationship between age and this other variable, which is, the other variable is cholesterol. So so that means if you're my age, then you better check your cholesterol level, because there's a high relationship or high correlation between someone's age and your cholesterol level. Okay, 0.84. Okay, cool. So then we come down here and Paul showed how you can plot with a confidence band, and we're going to see how we do this. So this is doing the scatter plot with a line of best fit with the confidence band, the lower band and the upper band. And that was why it was very important to know how to compute those confidence bands. Okay, once you have them, then you can easily fit them on your plot. But let's see how this is done. First thing you're going to do is, boom, you're going to read your data and indicate where it's coming from. Okay, from the pandas. A method called read Excel. So let's run that, and we're able to see the data. If we want to see just a few more lines, line 3 will give you that. I like display. Display gives you a much better output than print. I always like display. Print when I'm printing anything else, but when I'm doing a data frame, I like display. Display nice. Okay, cool. So then we know that this is a data frame. So then we are home free. Now what the developers who developed the method for fitting lines, or computing this line of best fit, are engineers, and we have statisticians who normally would do the fitting. So there's a little bit of disjoint, and then the way the engineers think is different from the way the statisticians think. Engineers are looking at the thing and saying that, hey, this thing is in a column. Okay, it could be that you have a regression which is not just X on Y, but it's going to be it's not just Y on X, but it's going to be Y on X1, X2, X3, X4. So whatever we implement is going to take something called like a multi-dimensional vector or multi-dimensional array. So if you just take the data as is, okay, if I take this data as is, because I need my X and I need my Y to fit my regression, okay? So if I take my data as is, like that, see what will happen. See, I have an array, okay? Now, at times, the method doesn't take an array. It probably just takes a list, you know? So you may want to look at what the method takes and then decide, and even the shape. Okay, so this is more like just like a 1D array. But then the guys in engineering want the thing standing up, because if you take things like neural net, things are fed in a column form. Okay, and that is why this comes handy. This took me time. There's also the reveal will do that, but this I like using this. Okay, so you see something like reshape 1 minus 1. When you see that, take time, look at what the data does, and then look at what the reshape also does. So in this case here, I'm going to do this, okay? And then I'm going to see how the two actually, how different the two are. Okay, so without the reshape, we know that we get an array. Now with a reshape, see what happens. Oops. Double. There we go. This was one of my frustration when I was learning Python. This was, so It took me like a month just looking at the data types and visualizing them. Okay, visual. Once you get this, the rest is a piece of cake. The rest is just a piece of cake because just a method. The method takes data of a certain structure, and then it gives you a result of a certain structure. So if your data is coming from statistics, and if the data is in an array, and the method that you're going to run, the linear regression method that you're going to run, expects trends to be in an array of a certain dimension, then you're going to be in trouble. Okay, so this is the case where I was talking about. So you see that here it's saying that it's a one column with one element. It's a column vector and only one element in each column. You could have multiple. You could have like 46, something, 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 20, something, something, just like we saw in our earlier example. Okay, so and this took time. This took me time. You'll be getting errors that can drive you nuts. Okay, so we want the X, we want the Y. If we get the X and the Y in the right shape, then sklearn, okay, has a linear regression model that we can use for free. Otherwise, we have to go through this computing all these statistics, all these values to get the R squared, okay, or even to get our equation, the coefficient of regression. And we have to compute them by hand. Okay, now once we use this, we get our data, we use it, then, and you see I do a lot of class. I do a lot of class. I want to see what is coming out. I want to see the type. I want to see a little bit of it. And then once I'm able to see that, I'm like, okay, now I got it. I know this is how my linear regression from sklearn expects the data. It wants the data in a block form. Wants the data in a block form because they are not only doing it for X and Y, they're doing it for X. Sorry, they're not doing it Y regression on X. They're doing it for Y regression on X1, X2, X3, Xn for a multivariable type prediction. Okay, and that's what I'm talking about. So this says that this has 25 rows, only one column. 25 rows, one column. Okay, so I take X regression Y. It could be 25 rows, 3 columns, and that could be X1, X2, X3. That means that my Y regression X1 plus X2 plus X3. Okay, and there's a reveal. This is another way of doing it. Reveal will do that for you. It will take whatever X is and make it and turn it back into an array. Okay, now let's speed up. So now we have the data. Let's see how we'll then fix it. How we would put it in a regression form. And it's really very easy. You call your library. Okay, so that's the first thing. You import, you instantiate, and you fit. 3 things. Import, instantiate, fit. This is true for all the fitting algorithms, including the machine learning fitting algorithms like long short term, neural net, SVM sitting, anything that uses this sklearn library is always importing, instantiating, and then you fit. And of course, you go and predict. Okay, so what do I mean by that? We've seen this before. Importing is just straight import. What we haven't seen is this here. Okay, so you're making an instance of a regression object. You define an object, and then you fit data on the object. And now you have a model, okay? And now you have a model. And then once you have a model, you can then use a model to do, you can extract your coefficients from the model. Let's see how that works. So we take this guy, okay? Let's take this guy here and then put it on top. And that's how I expect you to do it when you go back home. Just create more room here, take it baby steps. And I will just take this so that it looks much more cleaner, okay? So I have this, I take this very clean, just 3 steps, always 3 steps, okay? And let me take this guy out. so that the prints become the print, and then my prints go here. So the 3 steps here are the 3 steps you use in fitting a linear regression model. You instantiate, okay, and then you fit, and then you get a model. And what are these guys? Okay, so let's see what these guys are. So if you run this, it worked. Your X and your Y are now standing upright. They are not lying down. They're standing upright. So they worked. If you don't do that and you try to make the X and the Y stand any other way, you're going to get an error. Okay, so if I had used array instead of that array standing upright, I would have gotten an error like that. Okay, and it will tell you that the shape of the variables are not in the right shape. Yeah. So the shape, this shape thing, you have to have it in your mind. You have to have it in your mind. And it, from time to time, Python gives you a way to do that, but just have your shape right. Have your shapes right before you throw it on the on these methods. Otherwise, it will take you stay awake all night. Okay, so now I have my regression. I have this. I want to see what these things are. So let's see what that regression is. That linear regression, what it is. Okay, so you see that this guy here is a linear regression model. Okay, that's the type. And the model itself is this linear regression function or method. We have a method, so you can throw, once you have open parent, close parent, it takes arguments, okay? And that's where you do your fitting, okay? So you fit, because now you have something that's ready to eat, you feed it input, and you get an output. So now I have a model, let's run that and see. So I run that on here. Let's run this. Let's fit it. I think it's already fit. Yeah. Now, once you fit, just print it. Print and see what it is before you start putting in a nice put it in a nice output form. Okay, it has no summary. So then, what do we do? So you start, and then you start. Once you get here, you start, right? So what do we do from this point? And that's where Google comes into play. You have something that contains something that you think you need. How do you get to what you think you need? Okay, so Google around, play around, and you get it. But what I did was I went in, and I'm able to say that that model actually has an intercept. In fact, depending on the editor you use, you can actually see your variables. You can view your variables. I'm not seeing that here. I think Codio might have it, but certain browsers allow you to actually inspect your variable. So then you'll be able to see that that regression thing has, that model has something called intercept. Okay, so if we come down here and I say, show me the intercept, has a value. Okay, so I know there's an intercept value, and there's also something else in there. So just explore around, see how you can get to the variables in this object, and then just print them out. In my case, there's a coefficient and the intercept, and those are the things that I'm interested in. Okay, so I have the coefficient and the intercept, and then once I have the coefficient and the intercept, then you can actually compute the score. I mean, the root mean square error, which is just how far away your estimate is from the true value. And you can compute a whole lot of other things. Okay, so this is just here. This is FYI. In the interest of time, I'll leave it, but I've given you an example. So here, I'm able to do my prediction. Okay, so I have my prediction and I have my original. So then I can do a whole lot of things to that. Okay, so I can put them side by side, which is one way of doing it. Put them side by side. Okay, primarily I have my prediction. So, and I use my reval. Remember, I want to make it so that it's more like an array instead of standing upright, because the data frame now is going to make it stand upright. And I don't want the decimals. Okay, so I do the same thing for my Y and my predicted, and I have that. And I take a look at just a few lines of code. Now, once I can do this, then the sky is the limit, right? You can also see how the true relates to the predicted, how your model is actually doing. And all it is I have my true, I have my predicted, I go back to Dr. Musa's notes, and I know I can do PLT plot on the true values, PLT plot on the predicted values, give it a color, give it a label, and boom, I have an apple. And then I throw in the grade. Okay, so this always plot your things as you go. So this is telling me that it's doing quite a good prediction in here. It's matching the pattern. Okay, 1:30, we have 30 minutes. Any questions, please? We do another 15 minutes, and then we can just take a break. But let's go through so we don't run out of time. Okay, now there's another part here where I just wanted to just see how so this primarily doing a linear model on a data set using just as a challenge, right? I can do what I have. The more practice you have, the better you'll be at it. Okay, so this is just a challenge that says, hey, plot a linear model to the data. Okay, so just go through Google, or go through Professor Musa's notes. I have my X, I have my Y, and I just want to do a scatter plot. The aim here is that I want to get something similar to what Paul has here. Paul did something like that. Okay, something like that. I want to plot this. Okay, just out of curiosity, I just want to plot that. I have my X, I have my Y. I know he's using the dark red color, so I should be able to plot and get something close to that. And that's how you do it. Okay, so if we run this, we'll get something very, oops, I don't know what happened here. So I've run, unless maybe, I don't know what happened here. I might have changed, but anyway, go back. It may be that I don't have good data. I'm not sure. That's my X. Oh, there we go. Let me change this. Yeah, I don't know what. This is just so I'll get something similar to what Paul has. I broke it at some point. So go back, look at it, and make sure you can get something like that. Okay, so I wanted something very, very, very similar to that. Okay, so that's what this guy is doing in here. And I think I messed it up. But in the interest of time, we'll keep going. I'm doing some more plot in here, with a plot being defined now as a function. Okay, so now I'm going to define the plot as function because now I'm good at creating plots. And so I want to capture it as a function so that I can use it for other projects. I don't have to do a cut and paste. Okay, so here, if you see clearly, my plot takes a model, it takes an X and a Y. It asks whether you want the intervals plotted, okay, which is the confidence band. Okay, so primarily, I know my model, so I can do my predict to get my predict. If I predict, now I know my Y, I know my predict, so the sky is the limit. I can create my upper bound and my lower bound. Remember, these bounds are computed from sampling with replacement, right? So now in sklearn, you can do something called cross-validation. Okay, so you're doing a cross-validation in here. Okay, so this will give me a sample, and out of the sample, I compute a statistic and plot, or hold on to it, compute, hold on to it, and then plot. Okay, so let's do that. Okay, so once I define my function, then I can come in here and run the function on my data, okay, and just plot. So let's run that. Okay, and once I do that, for the data that I have, I'm able to do the upper and lower confidence bound and the true and the predicted. Okay, so this might be a little bit heavy, but it's there for you as a reference, and it all comes from Paul's notes. Being able to, once you are given something, replicating it is much easier. It might take you more than a day, but you have an end goal, so it should be easy. And once it's easy, put it in a function. Okay, so we have a challenge here. You guys will do that, and then tomorrow we'll look at it in the TA session. If you look at slide, we want to be able to get a plot that's similar to slide 54. So if you come to the slide 54, you want to get something that is similar to that slide. Let me go down here. So slide 54, I think this is the Bayesian. Oh, this is the Bayesian. Sorry for that. And then we also have something as far as the Bayesian goes. Let me go to the other one. So this one here, yeah, slide 54. So we want, yeah, so we want this. We want you to do this because now you have the bound. You have a way of computing the upper and lower bound. Just give it the data, give it a model, and it will fit it for you. Okay. So this time instead of this non-linear, you have a linear. So primarily, if this function works, then I can just give me the model and go in and change the data, and you should be able to get something similar to Paul's. Okay, so that is a challenge question there. Here, I was trying to compute some of the statistics that Paul has on his notes, and just looking at it. So this is just FYI, don't worry about it. And then Paul, if you remember, Paul did something on the Kaplan-Meier on slide 60. Okay, so that Kaplan-Meier slide, incidentally, Python has that. So just know what it is. So go back to the notes, look at it. Okay, so the Kaplan-Meier, I think we said is 60. Yeah, this guy here. Okay, you are given the values, and this is what, yeah, this is what I was experimenting with. When I take, if I take, I wanted to make sure that I'm getting these values. Okay, but if I can get those values, then I can do everything primarily. Okay, so that is what this thing was doing in here. Oh, sorry. I think I clicked it too fast. Okay, I clicked it too fast. Kaplan-Meier. Oh no, let's go back. I think I went back. Kaplan-Meier. Yeah, here. Okay, so this guy here, I was just doing from Paul's slide. I wanted to make sure that when it's 74, I'm getting the same value. Okay, and you can see that I'm getting 0.9865. Okay, so I was trying to get this. One death and then 74 patient. So the cumulative survival will be 1 minus that. That's that. Okay. Now the next thing is this here. How do you fit the Kaplan-Meier? The Kaplan-Meier plot that Paul showed us. Paul had a much better clean one. Google around, you see it. I got something that looks not so clean, but still, I don't have to struggle. There is a library that does that called the Lifeline. You have 2 data sets, and then you just remember that. Remember this. You create the object, and then you fit. Okay, create the object, fit. Just like the linear regression. So when the student was saying, I was like, all you need to know is you need to know the data that the method expects. If you know the data that the method expects, it is creating the object and then fitting it. Okay, create, fit. Okay, this is what we call instantiate. Instantiate, you fit. And then once you fit, this model here can then be plotted. And you can indicate whether you want the confidence interval or not. So if I hit this, I get a plot. And if I say show at the confidence interval, and I get this, it doesn't look cool, but it looks quite close to what Paul has. Okay. And this doesn't look any different from the linear regression. If you look at the linear regression model, you instantiate. Okay. So there's always the instantiation here. And then you fit. Instantiate, fit. Load library, instantiate, fit. This holds true for everything, for random forest and all those other algorithms. So it's always 3 lines of code. Import, instantiate, fit. And then of course, if you want to do predict, you predict. And then you can plot. Okay, so once you've done that, then we're done with that. Okay. And I'll give you some references here as well. So at this point here, you are done. And then we'll go to the non-parametric. And the non-parametric, in the interest of time, we just speed it up. So this is a case where you're doing something like leaving one out. Okay, so the other one, the bootstrap, you don't leave anything out. You put it back and take. In this, leave one out. Oh, so there's a bootstrap. Yeah. In the other one, in the next one that we're going to do, is going to be you leave one out, type 10. Okay, so here it talks about the slide, to give you a slide number, and it talks about what is being done. Okay, so here we're creating the bootstrap. We went through the bootstrap. This is just a reinforcement. The main thing with the bootstrap is know that you are taking a sample, you're computing a statistic, and then you are holding on to that statistic. So to hold on to that statistic, you have to define a placeholder for that statistic. Okay, so the mean, this guy, I haven't created it, so I'm going to have to make it blank. The number of samples is 5. The number of replication is 10. That means my loop is going to go 10 times. Each time I'm going to get a bucket of size 5. Okay, so in one line, because now we are experts, we're doing one line things. Okay, so now once I have that and I have this for loop will just populate this guy. Okay, so if I take this and I stick it up here, okay, so now this guy will have something now. Let's go to the next slide. There we go. So this is the mean for sample 1, bucket 2, bucket 3, bucket 4, bucket 5, bucket 6. Okay, so this guy here has created the means. So from here, you can create a mean of the means. Okay, and that's the bootstrap mean. And then you can create a confidence interval. And the confidence interval is just a pointer. And this also came when I Googled around that you can create a 25th percent confidence interval and then 97% confidence interval. And then once you have that, you just put them all together and you get something that looks like this here. Okay. You have the bootstrap, the mean, the confidence interval, your lower and your upper bound. Okay. And you see that your mean is within the confidence interval. Okay, cool. So just take your time, go through this, try it out for a different set of sample and document what you observe. Remember, Professor Paul said, if the sample is big or you take enough sample, your sample estimate will be very close to your population. That's what this is trying to see if to verify actually that if you do it for more samples, your true and your estimate will be closely matched. Okay, cool. So now we go next to the next set, and this year we just computed standard deviation and the mean just to get ourselves acquainted with some of the things that we saw. We take in a seed, we take in a sample, and then we just creating the mean. Okay, so just run this, and you see that with bigger sample, the population comes close to that. That's all this is doing here. Okay, cool. We'll leave this here. This is still part of the bootstrap, just reinforcing that. And then there's a challenge question here. We want you to do the 95% confidence interval for the bootstrap for the DBP data that we saw. Okay, so the code is in here. And so just try and then compare your output with the code. And the jackknife. So the jackknife is another way of really doing something like what we call the cross validation, right? So you have data, and each time, instead of taking the whole sample, you leave something out. So this one, I'm leaving one thing out. This time, I'm leaving this thing out, and then I compute the statistic. So you do that, and at the end of it, you do what we just did with the bootstrap. So the difference between this is that you are leaving one out. And the difficulty is how to implement that leave one out. If you're able to leave one out, then the rest is just using what we've seen upstairs. Okay, so let's look at it. So this is saying that you leave one out, you compute, you have a sample. You leave one out, you have a sample. You leave one out, you have a sample, like that. Okay, so how do you do that? Now to do that is very similar to what we did up there. You define your mean as empty because I'm going to populate it. Number of replication is the length of your your data set, okay? Because here you see that we're repeating it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's the length, okay? And each time, okay, if you look at it very clearly, you see that all we are doing is when I is 1, okay, assuming we flip this. When I is 1, or going from the bottom up, we leave the item in the first index out. When I is 2, we leave the item out. When I is 3, we leave it out. When I is 4, we leave it out. That's all we're doing. So then we use the index to exclude the item that we don't want to include. Okay. So we're saying that go from 1 to the length of your the number of times that you want to replicate, okay, which is the length of your data set. It could be 3, it could be 4. Each time when you are on that index, don't include that. Okay, so here, if I say BDP and I come down here and I say BDP of let's say index, let's say BDP of, let's say 1, 2. Okay, then what is going to happen is I'm going to get those 1, 2. But if I say, look, don't use this guy, then, oh, sorry, the index not equal to, I think not equal. If I say the index is not equal to 1 or 2, yeah, so index. Yeah, I'm tricking in here. So the index actually is more like a list. Okay, so if I say something like this, index equal 1, 2, 3, and then I say index not equal to 3, you see, what's going to happen is when I is 1, the index is not going to be 3. So to say, yes, the index is not, when I is 2 is not equal to 3. When I is 3 is equal to 3 and it's going to be excluded. So that's what we're doing in here. We're checking to see that the index is not the index, which is the set of numbers in that replicate that we are using, right? So here we're using the number of replicate as equal to, so the replication equal to 5. So do it just as I'm doing it, because if you try to do it all together like that, it's going to give you a little headache. So take your time and do like that. Okay, so if the replication is 4, then I get 0, 1, 2, 3, 4. 0, 1, 2, 3. If it's 5, then I'm going to get like that. So all I'm doing here is that I said, if the index, as you go through 1, 2, 3, 4, 5, if the index of the sample, okay, the bucket position is not equal to your loop indicator, then take the sample. Okay, so I'm taking the sample. So this is the only difference that's happening in here. In the bootstrap, I wasn't adding this. I wasn't adding no equal. I was just taking the sample with that set of index, and then I'll just computing it. Here, I'm excluding the index, and then from there on, it's straightforward. Compute the mean, append, and keep going on. Okay, so if we run this, then you're going to get a sample that looks like that. So the first time we leave index 0 out, this is our original data. If I leave index 0 out, then you see my data starts from here to here. Okay, so the difficulty is setting your sample up. Okay, now once you visualize your sample like this, and then you compute the mean. Okay, so the next time my index is equal to 1, so then I'm not going to include 50, 51. Remember, in Python is 0, 1, 2, 3, 4, 5. I'm not going to include 59. So I'm not going to include 59, and then I compute my mean. So the next time I'm not going to include the third item, and then I compute my mean. Okay, so now you have your mean being computed, and you are holding on to those means in the bucket. Okay, and this is the main thing, the juice behind jackknife. Okay, the jackknife says leaving one thing out, and then you computing the statistic based on the sample that comes out of it. So now we've shown that we're doing the right thing. So then at the end of it, we just compute the mean of the means and got what they call the jackknife estimate. In this case, the mean of the jackknife estimate of the mean of the population is 76.3. This will be different from what the bootstrap gives you. Okay, but There are references here. Please take a look at it. The difference between Bootstrap and Jackknife is listed in here. In the interest of time, we only have 10 minutes. So let's keep going. And now this is what Paul did today: specificity and computing the recall. Okay, so here you do the same thing. You have sklearn has something called a recall, and all you do is you pass it two lists or two numeric values, and it's able to compute the score for you. Okay, and that's it. And then you can do your confusion metrics. Okay, remember Paul did this slide, today's slide 15. All it is know where to get it. You know, it's already there. Just know where to get it and what to pass it, and then it gives you the plot. It gives you the things that has to be in the plot. Now remember, my data look like this, and if you look at this, when it's true, so primarily if you lay this out the way Paul has it, and you compute it by hand, you're going to get something, a confusion metric that looks like this. This is the true. This is true when it says it's true. Okay, and if you look at it, true when it says it's true, how many times does that hold? One, it should have been 3. Now, if you arrange it well, 1, 2, 3, or something like that. Yeah. So just take a look at it, and you'll be able to reconstruct this. Okay. So this is how the confusion matrix is constructed. Oh, sorry. I think we are almost done. Yeah, 9 minutes. And then you can even do some more before you plot. Just take a look at it. Okay, take a look at it, and then once you've taken a look at it, you're sure of what it is, then you can do what you want to do. Okay, so this is what Paul used in one of his slides, and there's something called pre-confusion that comes from the PP matrix. You have to install it. Okay, install PP matrix, and then once you install PP matrix, you can then run that, and you'll get something similar to what Paul had. Okay. So if you compare this to Paul's confusion matrix for today's slide, so this is today's slide that Paul had, there would be something on the confusion matrix that he did. I forgot to indicate the slide, but if you very much recall, you would have it somewhere here. Yeah, there's a guy. Okay. And the sensitivity, specificity, and all that will be computed for you if you know how to lay it out. Okay, so that is what I wanted to show today. There will be more. We'll post this. On as I clean it up, and then we'll see you guys tomorrow. It's almost 8 minutes to time. I'll leave the next 3 minutes for questions, and then we'll leave the next 5 minutes for your checkout and for John to give the closing statement. Okay, so the floor is open now. If you have any questions.
So any question for Williams?
Hi. Good morning. I apologize. I hear it was a little bit technical. I'm not sure how I connect to the microphone amplifier at home. Yeah, sorry. And I think at least an hour of the talk, I didn't realize until I checked my calendar what was in the same Hawaii time. It's summertime now already. So.
Is that a question? Looks like a lot of background noise.
Yeah. So can you please put it in the chat? Because we didn't catch what. I think he's apologizing that he wasn't able to make it on time and that he didn't see the link, if I'm right.
Okay, so the links are reposted. So if you want to sign in, Stacy just posted the link again. Also make sure you complete the evaluation. Again, as I said, your feedback is very important to us. So again, let's thank Paul and William for 2 days of excellent presentation of overview of statistics and the Python codes to evaluate some of those. We'll continue with this next week for more statistical concept and also how to use Python to do those. So again, thank you all for your participation, and then we'll see all of you again next week. Also, there will be TA sections tomorrow. If you want to participate, just check Slack for the link. And then if you have any questions, you can put that also in Slack. So if there are no further questions, then I wish all of you a great weekend, and then we'll see all of you again next week.
Thank you.
William, looks like there is a question in
the Slack?
No, in chat. In the chat, is the instructor solution available in the folder?
Yes, in fact, it will be available. It is available. It's called. It's the same thing with solution tagged to it, but the solution will be out of date. So we're going to post that tonight. And then Paul also had one slide that would also be posted. So the Bayesian slide will be updated, and then the instructor solution will also be updated. Because some of the things I was just doing it as Paul was going through.
Okay. Yeah, so again, I think the idea is to check Slack for any updates on the lectures and other things. All right, so again, looks like everyone is tired. I can understand it has been a long day, so take your time, relax, and we'll see you again next week.
Okay, thank you.
All right, thank you, William. Thank you, Paul.
Thank
I don't know if Paul is still around, but thank you.
I think Paul is gone.
He's gone. All right.
Okay, John. So yeah, we'll touch base over the weekend.
Sure.
Yeah,
All
okay,
right.
thanks.
Okay. Bye-bye.